the floor. Good morning, students. This is Professor Joshua Ojo, Department of Physics. We are continuing our discussion on gravitation. This is the last segment of in our topics for Physics 101. And again, I'm sorry we are starting late again today. And even we have about 40 minutes for this whole thing. But fortunately, you have the slides, and so please make sure you go through them. So yesterday we saw that the major thing about gravitational force is one of the four fundamental forces in the universe. So, and it's at large distances, it is the major one. Within molecules, the EM force is predominant. Within the nucleus, you have the strong and the nuclear forces. So what did we learn about the gravitational force? The basic thing is straightforward. The force, the extent of that force is please let me start with the marker. The force is G, which is a very, very small constant. The product of the masses, okay. The force is G. The product of the two masses involved, and square of the distance between 1 and 2. So that is all we were looking at yesterday. We look at various aspects of this equation. When one of the forces is the Earth, for instance, such as gravitation on Earth, ME, then you can find, then the R, the distance will be from the center of the Earth to the altitude at which the object is. And we saw all of that. Finally, we saw that for the Earth, what the acceleration due to gravity that you measure is not necessarily what you calculated, is not necessarily what you measured, because that is moderated by 3 factors. Number one, the fact that the Earth is a geoid and not a sphere. So at some places, the distances, the radius are not exactly the same thing. So number two, the density of the Earth varies. So the M for the Earth is not uniform. So that can affect what exactly you are going to feel, apart from what you just calculated based on the spherical uniform Earth. And thirdly, we saw that the Earth is rotating. So the rotation does not affect the G equals to M1, M2 over R squared. But something moving in a circle, if you have an object here on say at the equator, it's easier to calculate for the equator. It's rotating. So obviously, there is a force towards the center. So that force, we know it to be mv squared over r, which boils down to m. V can be m, that's omega r. So we saw that. But in this case, the direction of that force depends, use your right hand rule. If you call your finger, the thumb will be pointing at the direction of the force. So in this situation, we know the magnitude is mv squared over r. The direction is given, so the Earth is rotating eastward. So actually, this force is a centrifugal force. It's pushing away. So at the end of the day, is reducing the intensity of the gravitational force. And we saw that equation yesterday. So now we want to move. It's the same equation we're looking at. F is G M1 M2 over R squared. Now supposing, what happens to gravitation inside the Earth? Inside the Earth, the section of the Earth that is outside the particle does not contribute to the M. That is the only thing there. So you got to find out what is the mass. So the force is, this is the equation. F is G, M inside, all over R squared. So to calculate the M inside, you can just, if you assume if you assume that the density is constant, so you can see the density is mass over volume. That's m inside over volume inside. And that's the same thing as total mass over total volume. So if you look at that, this equation, so you can now substitute back to replace m inside by this value. So at the end of the day, what you get is all these constants, because G, M, big M, R cube, R, they are constant. So what do you see? F equals to minus KR. So this is the first is Hooke's law. So that means within the Earth, as the object is moving, if you are tunneling, for instance, towards the center of the Earth, the force you get is like you see, like Hooke's law. It will be increasing as you move towards. You can see it. What are the factors contributing? The mass of the Earth that is involved, that mass is decreasing because the mass outside does not contribute. But the radius, the distance, is decreasing. But the decrease in the radius is squared. So it's contributing faster than the mass effect. So at the end of the day, you can see plainly this equation of an object moving. This is how the gravitational force varies within the Earth. I hope that is clear. So now we want to talk about something important, potential energy between an object on Earth and the planet. And the two objects, there's gravitational potential energy between them because they're attracting themselves. So if you move one object, say your apple, you move it, you're trying to move it away from Earth. You need to do work. So you are doing work because the Earth is pulling it back. So the work you do is, of course, F dot R. And so if the F is varying, you integrate F dot dr, which of course is FR cos theta integrated all over the place. The bottom line is this: if you do that, if you assume the force is constant, gravitational force is constant, you get that you will get this simple equation. U, this is the potential energy, is minus G M R. What you note here is that it's now R instead of R squared, because the force itself is G M over R squared. If you integrate that dot R, so this is what it comes to. So just note the final answer, that the potential energy varies inversely at the distance, not at the square of the distance, because it's just F dot R. So, okay. So if you get that, that's about all. So you can see this topic is straightforward. We have considering the equation that Isaac Newton gave us. The force is G M1 M2 over R squared. And we have looked at various ramifications of that particular equation, inside, whatever. And it's always between a pair of particles, two particles. If you have more than one or two, a million, you add vectorially. The same thing goes here. Between every pair, there's a potential energy for a two-particle system. And it is very simple, minus G M, the other M, over R. Now note the minus, because it is a negative energy. That is why it is attractive. Let me ask a question, try this. Minus 20 and minus 40, which one is bigger? Can you try that? Minus 20, minus 40, and 0. I give you three numbers. Minus 40, minus 20, and 0. Which one is the biggest of the three? Sorry, I can't get your response from here, but you can check for yourself. Minus 20 is smaller, is the least. 0 is the biggest. So when you see this potential energy is negative. So the further they are, the smaller the magnitude, the bigger the potential energy. So as they're coming closer, you can see that that value we have will come to 0 at r equals infinity. At infinity, if you infinite separation between the two particles, m, big M, and small m, the u will become 0 at that point, and that is the largest value. But in magnitude, of course, 0 is smaller. Long and short, there are two points to note here. Number one, you can see from this diagram here, if you have a 3-particle system, the potential energy of that system has to be calculated for each pair. So like in this case, let's take particle 1 as our reference. The potential energy of this system will be the potential energy between particle 1 and 2, and then plus the potential energy between particle 1 and 3, plus potential energy between particle 2 and 3. And you can see the equation here. Everything is just G, M1, M2, all over the distance between them. Just add, and in this case, it's a scalar. No complication, just add the value, and you get the potential energy. So that is clear. The gravitational potential energy is between 2 particle systems. You have lot of particles, you calculate for each pair, and you add together like a scalar. The second point is this, and this is important of practical application. If you want to remove one of the particles from that system, you want to dismantle the system. So you have a 2-particle system, you want to dismantle it. How much energy will you need to put in? That is the question. So how much energy? You need to put energy that equals that potential energy. So in this case, if U is equal to minus G, M, small m over R, so if I supply that amount of energy, the total energy will come to 0, and the other particle is free from the potential, from the gravitational influence of the big M. So that is what works. This has a practical application when we discuss what we call escape velocities from planets, for instance. Okay, from this chart, you can see that the gravitational force is conservative. It does not matter the distance, the path you choose. If I'm moving something from one height to another height, what matters is the height. It does not matter if I move around the clock like this, like you see in this something. It doesn't matter. What matters is the initial point and the final point. So you see that force is conservative. So yeah, we are talking about what we call the escape velocity. So if I want to throw, like I want to get a rocket out of Earth, or I want to throw a stone, to get it away from the gravitational influence of planet Earth, I must supply the potential energy that is binding that particle to the Earth. If I supply it to that object, then it can be free. So we call that the escape velocity. The escape velocity is the velocity which it has that will make it to escape the planet in question. And it's very straightforward. You just give it kinetic energy, which is equal to the potential energy holding it. You can see from that equation, K plus U, let one is 0, or this half mv squared, which is the potential energy, kinetic energy, equate that to minus to gmm over r. If you solve for v, this is what you see, and that v is the escape velocity. Note that it does not depend on the mass of the particle you are throwing away. The mass of the rocket does not matter does not come into this equation. What matters is the G, gravitational constant, and the M, the big M for the Earth. You can do this. This has been calculated for other planets, the Earth, Moon, all these planets, other bodies, Jupiter, Sun. It's the same thing. That's the escape speed. Again, how do you calculate that? You give it sufficient kinetic energy to overcome the potential energy. The gravitational potential energy is G M1 M2 over R. So you must equate that to half mv squared. So the v that you get there is the escape velocity. I hope that is very clear and it's straightforward. So let's move now to other factors, other issues. So you can see this. Now we want to apply all this to planets and satellites. Kepler's law. We have a lot of issues trying to understand the movement of the heavenly bodies. So you have planets. Planets are natural satellites. That means they move around a major body. The name planet actually means wanderer, something that is wandering. And our predecessors, they had issues trying to understand. So you have Tycho Brahe, who took very, very meticulous measurements, and you have Johannes Kepler, who was able to look at those data and come out with three planetary laws. So we are talking about three Kepler's laws. So let's just go ahead. The first law is talking about the orbit, because the planet is a wanderer, it's moving around. You can see the diagram here on the left. It looks complicated and whatever, but look at the data. Kepler was able to convincingly show that the planets generally move in an elliptical orbit. And you can see an ellipse here. So what's an ellipse? Ellipse is just like a circle that is elongated, flattened. And so an ellipse has two foci, a focus 1 and focus 2, those two foci. And the distance, the two foci are separated by a distance, which is the, what do you call that? So there's a major axis distance, kind of. So, and you, from the center to one of the foci, we describe it as EA, where E is the eccentricity of that ellipse. So these are just what we use to describe an ellipse. And you can see that if the eccentricity E is 0, then everything will collapse. That means the two foci will meet at the center. So for a circle, the eccentricity is 0. But generally, planets move in elliptical orbit. So that's actually the first law that Kepler came up with. All planets move in elliptical orbit with the sun at one focus. Of course, we are talking of the planet in the solar system. So the sun is the major body that they are moving around. So that's for the planet. So the law of orbit. So the orbit is defined by this semi-major axis A and its eccentricity. So the eccentricity of the Earth orbit is 0.0167. Please note that figure, 0.0167. If it was 0, it would be a perfect circle. If it were longer, then it will go, the ellipse will be. And as it moves around, you have points where the planet is closest to the sun. Let me move back up one slide. Near here, this is the perihelion. And here, this is the farthest. So this is the closest to the sun. And here, the farthest to the sun is the other aphelion, I think, aphelion. So note that. Having seen that, so the first law of orbit is that all planets move in elliptical orbit with the sun at one focus. The second law is sometimes called the law of areas, and it's essentially law of conservation of angular momentum. And it says that the line that connects the planet to the sun sweeps equal areas as it moves around. So equals area, the ADT is constant. So essentially it means the angular momentum is so you can see from the diagram here, the planet sweeps out this area. So the area it sweeps out is constant, the same pattern as it moves around is constant. And the last one, the third law, is that it relates the period. The period is the time taken to complete one orbit. So that period is related to the distance, the semi-major axis. So which we have here. What we have here is for a circular orbit. T squared equals to, all of this is a constant. 4 pi squared gm. So it's a constant. So T squared is proportional to R cubed. That is what you should note. T squared is proportional to R cubed. And if you want to generalize for ellipse, you change this R to A. So T squared is proportional to A cubed. That's the third law, the law of ellipses. So, and you can find on that table various periods for planets in the solar. You can note one thing, that these values, that is T squared over A squared over A cubed. T squared is proportional to A cubed. So you can see it's almost 3 for all of them. So let's move on. So we can look at the orbit, the energy between them, the potential energy, just like we saw earlier on. It's quite straightforward. You can find the kinetic energy, that's half mv squared. You have that. If the orbit was circular, then it will be half mv squared over r, which gives us this value. The total energy over 2 is the kinetic energy. And the total energy, if you use what you had before for potential energy, if you put it inside here, you can find that this is the energy for a circular orbit. As I'm beginning to close, because there's another exam going to happen here shortly. You can see, but note is the total energy is negative. So total energy, and importantly, it is independent. It does not depend on the eccentricity. So for the same, what matters is the size of the orbit, not the E. So in this diagram, the eccentricities are changing. This E equal to 0, giving us a perfect circle, 0.5, 0.8, 0.9, and so on and so forth. But the total energy is the same. It's independent of the E. It's only the area of the orbit that matters, not the eccentricity. So this is a plot of the energy versus orbit radius here. The kinetic energy is decreasing. It's decreasing. Potential energy is building up. But all of them always add up to the same value. Okay. Finally, what we have described so far is what Newton gave to us, that when every matter comprises of mass, if anything matters, it has mass. And those two masses, they interact according to that equation, G m1 m2 over r squared. So it's like a basic fundamental law, and we just took it like that. And we call that Newtonian attitude to gravitation. But there are other pictures that are coming up. The first is Einstein's opinion, view. And the long and short of it is that what we call principle of equivalence. Einstein believes, and he shows, that actually gravitation and acceleration, they are the same thing. So that's called the principle of equivalence. Like I mentioned earlier on, when we look at the fact that the Earth is rotating, that rotation has nothing to do with gravitation from Newtonian point of view. It's just a motion. moving in a circle. If you are moving in a circle, there is a force. You are accelerating. So there's a force keeping it in a circle. Newton's first law says every object will go in a straight line, except there's a force. So the force that's keeping it in circular motion, turning around, is simply acceleration. And we saw that the direction of that acceleration depends on your right-hand rule. Okay. So Einstein is saying actually both gravitation and acceleration are the same thing, they're equivalent. And you have this thought experiment that you have demonstrated here. So that is the long and short of it, and it works. This is the way it works. The view is that space-time, we describe our physical universe as the physical aspect is space-time. They form the same entity because time is another dimension of space, as you learn later on. So Einstein's position is that when you have a mass distorts space-time. So that is the summary of Einstein's position. So it distorts, as you can see in this figure here. So it's like you have a trampoline or whatever, and you put a mass on it, a stone. So it will cave in, just like you see in this picture there. And if there's another mass nearby, you can see that it will just naturally be accelerated towards that something. So Einstein his view is that is what is responsible for gravitational force. It's not as if there's something that automatically causes two masses to jump at themselves, but rather the masses affect the space. And when the space around them is distorted, it affects their motion. They gravitate. In fact, that is where we get the gravitation. They gravitate towards one another. So that is Einstein's position. And that leads to what we call gravitational lensing. This is the final point I'm making. Gravitational lensing means, because that means light can also be bent. So you can see in this diagram, if you have a very, very massive object like a black hole, this is a black hole, and you have light coming in. You have light coming in ordinarily, but because this mass has distorted the space-time, the light can be bent. So if it's bent, like you see here, from what you learned from your optics in secondary school, light, as far as the eye is concerned, travels in a straight line. So the eye will assume that this light, this ray we are seeing here, is coming from somewhere here. It's coming in a straight line. It didn't know that it was bent. Same applies here. So it's actually possible to see the same object twice. All this. So, and that's what you see in this picture. The same quasar is a very big something light, massive, is due to gravitational lensing. It was bent around, and you see. So if it happens multiple places, I have 11 minutes. Let me give you the codes. Because we have 10 minutes. In fact, I'm stopping the next 5 minutes. Here are the codes, please. Sorry. Code 1 is 4FG85. 4FG as in federal government. 4FG85. I hope that is okay. I'll give you the second code also straight away. Second code is U6 SLN. S as for Stephen, L as for London, and N. U6 SLN. I'll give you the third code. Okay, no, let me give you so that you can begin to key it in, because the lecture will be running up in 5 minutes' time. The third code 3 is T as in Taufik, T X as in xenophobia, T X H as in height or height, Hollywood, So it's TXH KH. Code 3, TXH KH. Let me repeat. Code 1, 4FG85. Code 2, U6SLM. Code 3, TXHKH. Okay, so we've come to the end of our discussion of gravitation. We've seen that there are three theories, three perspectives, both are valid. We can't say one is superior to another. Concerning gravitation, we have seen the Newtonian. We talk of the source of gravitation. Just like I told you, the Earth is rotating. Nobody knows why it is rotating. How it's rotating. It's rotating eastward, and it makes a difference. If it were rotating westward, that acceleration, which we subtracted from the gravitational, would have to be added. It would be a centripetal one. All you have to know is it follows the right-hand rule. If you curve your hand in the direction of the rotation, where your thumb points, that is where the force is acting. So because the Earth, we don't know why, is rotating eastward. So if you move eastward, actually your apparent weight will be less. And the opposite effect will happen if you are moving. If you do the calculation, for the rotation of the Earth, it's about 0.35%. So it's very, very small. And if you put on your own velocity, is negligible. In conclusion, the source of gravitation is unclear. But so there are three possibilities. It could be a purely a curved space-time. The masses distort space-time, and that affects motion. It could be a force, Newtonian force, between the two masses, every pair of masses, or it could be due to a fundamental particle which is called a graviton, which are emitted between particles. So these questions are yet to be settled. I wish you all the best. The slides are available for you. The secretary will make them available. You can look in details. The textbook is Alidi and Resnick. You can check for details. And if you have any question, we'll be happy to get back to you. Thank you and good morning. Very much.